just sort of email in new verifiers. And I've never heard of this language, but someone decided to write a verifier in it. So we have 14 verifiers, which have been just implemented by many different people. And there's 2 major proof assistants, and there's a few others in development. The largest database of mathematics, and the reason why this was put under this category of systems based on set theory, is the set.mm database, which is based on ZFC set theory. So there's about 30,000 proofs in there, and I'm going to show you some of the stuff which is involved in that library. But there's also some on NF set theory, and it's also, MetaMath is pretty good for being able to handle a variety of, like a really large variety of different formal systems. So here there's some examples of other MetaMath implementations of different logical systems, including Hull and intuitionistic CF, dependent type theory, you know, like the way in which Lean does it, I tried to model, as well as a few more unusual ones doing like Hilbert spaces or quantum logic and the laws of form. So I'm not as familiar with some of these more unusual logics, but apparently they can be done in them. So the way it works is, so the reason for the name MetaMath is it's actually meta-variable mathematics. So you consider how a logician might write a formal proof, or what they would call a formal proof in the textbook. And so the formulas have some kind of, you have these symbols, you have arrows, and individual variables. There are no meta-variables in the actual ground logic. There are an infinite number of axioms, but these axiomhood is decidable. So you can represent this using a finite number of schemes like this. So you would say that any axiom which has this particular form, where you plug in things for phi and psi, is an axiom. So in MetaMath, we sort of extend this to theorems as well. This is an example of a simple MetaMath proof. So every step of the proof involves metavariables, and you end up with a theorem scheme. So since everything here has this sort of free metavariable phi in it, you can substitute it later. If you were to substitute in any particular expression for phi here, you would end up with the logician's formal proof in a one-to-one method. So the foundations are simple. The verifiers are very small because of the simplicity of the system, and also, and I think that this is not sold as much as it should, but the advantage of this way of representing it is that there's literally nothing which a verifier has. It just reads, it's almost as fast as reading the proof as verifying it. So you can write a verifier for something where the verification time is comparable to the I/O time of reading the file. So the whole set.mm database can, with one of our verifiers, be verified in about a second. So this is just completely not even comparable to most other verifiers or in other languages. So the axioms are user specified, so it's not tied to ZFC or any other logical foundation. And you can also track usage of axioms, which is important for being able to work within logical subsystems at the same time.
Sorry, you haven't yet said what the foundation is.
Yes, I actually will. So I'm going to say a little bit more about what has been done in MetaMath, and then I'm actually the main topic of this talk is going to be how exactly is MetaMath represented. So I think we can probably skip this. So here's an example of a few theorems which have been formalized in set.mm. So this gives you some sense of the breadth of theory which is in there. And here's a few more. So these are from the this MetaMath 100 list from Frank Videk.
Oh, it's not MetaMath 100. It's
Well, we call the project the MetaMath 100 project because it's the project to formalize the 100 theorems listed in MetaMath. And so we've managed to tie Koch on this one, so we're kind of happy about that. So the new ones here are actually these since last time I gave this talk. And here's some example. This is sort of the progress over time. All right. So what is so how exactly do you represent what MetaMath does as a sort of logical system? So you start with this basic conception of say set theory. So you have the universe of discourse. This is some set or some universe over which you want to talk about. The elements of this are set. And then we have an object logic which talks about this universe. So this is the expressions, the epsilon relations and all these equality. These are just expressions involving v0, v1, and so on. And they denote terms, or they denote formulas in referring to this universe. The meta logic works one level higher than this. So this is, now you have meta variables which range over the variables of the object logic. So MetaMath works at the top two levels, whereas first order logic generally works at the bottom two levels. So in first order logic, you want to understand how this relates to this. In MetaMath, we're worrying about how the meta logic relates to the object logic, and in particular, the universe doesn't enter into it, so it's only indirectly there. The meta logic, or the logic which MetaMath implements, is essentially that of string substitution. So you have these meta variables, and then you can insert any well-typed expression for it, where the typing rules are dictated by the actor. You can substitute in two expressions, and yeah, so you just have something at the same time. And in particular, just because two variables are textually distinct, like x and y, doesn't mean that they map to distinct variables when they have been substituted. So for example, with this formula, you see for all x, x equals y. Let's suppose that the universe has more than two elements, so that this would normally be false, except it's not necessarily false because it depends on whether or not x and y are equal. So, and when I say equal, I mean the same variable. So if they are the same variable, then it's really saying for all x, x equals x, which is true. But if they're not the same variable, then it says for all x, x equals something which is not bound, and then that will be false. So in order to model this situation of meta variables which are not supposed to overlap, we have disjoint variable provisos. So if two variables have a disjoint variable proviso, then you cannot substitute the same value for those two variables. And so now we can prove this first statement, that it is not the case that for all x, x equals y, if x and y are disjoint. And similarly, you can say that a variable and a well-formed formula are disjoint, meaning that the well-formed formula does not contain the set variable in it. And then with that, we can state theorems like this one, which appends a for all x in front. So this would not necessarily be true without that. So these are distinct from bound variable conditions. So with MetaMath, we just have these meta variables. We never actually go down to the object language. So yeah, each meta variable has a type, and yeah, so we can just substitute anything which has the right type, provided that it satisfies these disjoint variable provisos. So that's so sometimes it'll be said that MetaMath has only one rule, and this rule is substitution. So at each step, what you do is you take an axiom, or a theorem with meta variables in it. You substitute in some provided expressions for the meta variables, and then you check that the disjoint variable provisos have not been violated. And that is all a verifier needs to do. And so it does this many, many, many times, and it's just by repeating that process, you get all the theorems.
So you cannot even have a variable in the language?
Not like V0 from the previous.
Mm-hmm.
So you cannot have variables of the object language. What you can do is you can write a meta variable, and then you assert that this meta variable is, say, distinct from everything or distinct from whatever you want it to be distinct from. And then it will have the appropriate properties of first-order logic variable.
What are the types?
Hmm?
What are the types?
So there are. So I like to call these sorts because they're.
What are the sorts?
So set, WFF, class, and the turnstile. So theorems have the turnstile type or.
So there's
sort.
no structure on the language of types?
No. So, well, there is a very slight structure. So you can
So
say
I
that.
can't, for example, consider the type of functions that send meta variables to well-formed formulae or something like that. Or functionals that take a transformer from well-formed formulae to well-formed formulae and give you another well-formed formula, or you know what I mean.
Right. So yeah, this is a finite sorted logic. It does not have. It's not like simple type theory. So this is why I went to call them sorts, is because they do not have this flexibility. However, you can construct individual objects of that type. So let's see. I don't think I'm going to mention it here, but the for all. The for all type, you could say that this has a type which looks like set. So the idea is that this is a binary relation on type. So you can imagine that this has such a type because of the way it's been defined.
But it actually has what sort?
So the way this is actually defined is it's a rule which says something like x.
Oh, okay. So there aren't just meta variables. The for all is not a meta variable.
For all is not a meta variable.
So what
this,
what is the language? So we're sort of discovering it bit by bit. But
okay.
so there are meta variables. There's for all. What else?
No. This is not. This was defined as an axiom. We would say something, we'd say actually we don't say that. We say, but that means axiom. So this is where we would define inside the .mm file this.
But what I'm trying to get at is the symbol for all, does it have a distinguished status?
No. So it is this would you would say for all is a constant. It's allowed to appear inside formulas, and then you would define this inference rule within the file and declare it as an axiom. And now you're allowed to use for all.
Okay.
So it does not. MetaMath does not know anything about for all a priori. And there are, in fact, many of those logics I mentioned don't even have this or have some different way of implementing for all.
So I could write for all, even when x and phi aren't of type set and WFF, but then I wouldn't be able to infer that for all x phi is WFF.
So the MetaMath program will automatically infer these syntax proofs, which is effectively equivalent to type inference. But in order to substitute, so for example, in order to substitute something in for phi, I would need to prove this precondition. And so if you had something where it wasn't actually a well-formed formula, or you couldn't prove that it was a well-formed formula, then you wouldn't even be able to apply the substitution.
So it wouldn't even be parsed, basically.
I mean, you could write, I want to prove some statement that this thing is with poorly balanced something is and then I try to prove it, and then I don't know, how am I going to prove it, right? I can write it down, but that doesn't mean it's proven, and you're not going to be able to prove this theorem.
Yeah, that's fine. But for example, I could try it for all.
Yeah, you could write that down, but it wouldn't be. I mean, you're not going to prove that theorem.
Yeah.
So, yeah, I mean, in order to apply this, you have proof obligations, and if you can't discharge, you can write them down, but then you are just giving yourself impossible proof obligations. So, but actually, if you use MMJ2, it does this part of it automatically. So the parsing of statements is actually built into how MMJ2 handles the formulas. And so it will immediately, if you write this, it'll say, I'm sorry, that's not well formed. Usually it just discharges, so at least in set.mm, the derivation of these syntax proof trees is decidable, and we have implemented decision procedures for doing that. So obviously a variable is not disjoint from itself, but these two rules together give you everything that you need to know about how disjoint variable provisos propagate through a proof. And so generally when you state a proof, you will also state the disjoint variable provisos, or maybe in your tool will automatically generate them. But either way, you have some disjoint variable provisos at the beginning of the proof, and then the verifier has to check that everything that you do respects the disjoint variable provisos that you get. So I mentioned that.
That's so 19th century.
Well, so it has.
It's like abstract syntax trees of 20th century. We're now in the 21st century where we can do even better.
So MetaMath is in fact built on. So this is 3 characters.
Yeah,
this is not, or this is rather 3 tokens. So it tokenizes, but it is not represented as a tree, at least in the formal system. So this has some unusual advantages in some systems, like the laws of form actually includes empty substitutions as an integral part of its logic. So it has parentheses for not, and then adjacency for and then you just have these sorts of expressions in parentheses. It's very cool. But you can use the ability to parse one way and then prove it by another parse, and so there's some very unusual effects you can get if you're using if you're using ambiguous grammars. I don't like the complications that this gives me, so I can restrict my. I want to look at just the systems which don't have this property. Importantly, set.mm with all those proofs does not has the property of being well grammared. So it has unique parses for all of its syntax trees. And if it has unique parses for all its syntax trees, then you can just pretend as though everything is trees. So you can use a verifier which just reads these formulas and then parses them into a syntax tree and then works on those syntax tree representations. And I think everyone here understands the usefulness of being able to work from a tree-based system. But actually, the string-based approach is extremely fast. So I think that this is one of the advantages of continuing to have that sort of, at least at a foundation, is because you can just do string rewriting in order to prove your theorems, which is a lot faster than having to construct it. You've just got these big arrays full of tokens, and then you know that everything's going to work out because of the unambiguity of your grammar. So the way syntax is declared is through a statement like, so this says WFF x equals y, where x and y were previously declared as set variables. And so this is saying that whenever x and y, whenever you substitute in something of sort set for x and y, then you get something of sort WFF. So this translates to a context-free grammar in the following sense. So this can also be read as a rule for a grammar. So you would have for all, and then a set, and then a well-formed formula, or something else. So a production, so a single, this rule translates to a single production in the context-free grammar for well-formed formulas. So if you have a non-terminal here for well-formed formula, and this is non-terminal for sets, and then you would also have rules here for variables. So these are constants. So you can produce a context-free grammar from any specification of the syntax axioms, so these inference rules here, and then you can ask the question of whether that context-free grammar is unambiguous. Now it's known that unambiguity of context-free grammars is an undecidable problem. But in certain specific cases, you can prove it. In particular, you can prove it in set.mm, which happens to be the one that I care about. This is kind of an obligation, an unchecked obligation of the MetaMath system. If you want to be able to work, if you want to know that this alternative method of just parsing your strings rather than working directly on the string level, if you want to parse them into trees and know that that's going to get all of the proofs, that there are no previously good proofs which are lost by this method, then you need to know that the grammar is unambiguous. So I'm working on methods for being able to specify and prove unambiguity by, say, having a special kind of parser which can only parse unambiguous grammars.
Could you also show some examples how you really do something in MetaMath? Because like we have like 40 minutes each, so to really show people how you do things and how they look. I mean, I don't want to disrupt you completely. I'm just like saw this as a demo session. So
Yes, yes. I can show you how the MMJ2 proof assistant looks like. I'm not as proud of that because I sort of entered the development of this tool a little bit too late for me to
We won't mind.
You don't know what we've been through before.
Yeah. We know it's not your dirty washing, so
Yeah.
it'll be embarrassed.
Let's see. This is the actual proof assistant. So I prefer to show people the HTML versions of the pretty printed output, and actually we were discussing this week about a new way of presenting the HTML output, which is much closer to standard mathematical vernacular look. So I'm very happy about that. But on the IDE side, you still want to work with these ASCII representations. MetaMath does not like to use Unicode because it's difficult to support and to have it. Basically, it limits the ways in which you can do your input, and it adds a lot of complexity to everyone who has to deal with the thing. So it's much less likely that we're going to have random people just writing in and saying, "Oh, I wrote my own MetaMath verifier," if we're adding all these barriers to entry. So we're trying to keep the basis simple. So it is.
Just talk us through the buffer. So clearly, the left-hand side are line numbers.
Okay, so yeah, so
And
this
then-
presentation
then
format.
exactly what, as I read it.
Right,
So
so-
which is the theorem being proved?
So this theorem.
Which is the statement being
So the theorem statement is at the bottom here.
Oh,
It says that if A and B are natural numbers, then A is less than B if and only if B minus A is a natural number. So this E dot, that's epsilon.
Okay.
And then
And
NN
what if A
is,
equals B?
Huh?
What if A natural number starts with 1?
these natural numbers start with 1.
Oh,
Yes, we
okay.
have an NN 0, which is the natural number starting at 0. Yes, I realize that wars have been fought over this. So, yeah, I'm not even sure which side I'm on. But
It doesn't really matter.
but yeah, this is so this is a sequence of, so the way you read this is there's a sequence of steps where each one has these. So this is the statement of this line of proof, just like the previous view where we have these lines of. So if this were dependent type theory, these would be like the types of all the terms.
And these are all things that start with turnstiles, so these are all theorems.
And these are all theorems, yes.
Yeah.
And in
But
fact,
you could have some other lines that might be woofs or.
so technically, in the output proof of this, there are actually many lines which start with woof and set and so on. But these are all elided and proved automatically by the system. So that's because of what I said about the typing being decidable. So it just does all those syntax proofs on its own, and you don't ever have to give it any hints about anything. But yeah, so it shows you what it does show you are all of the theorems in your proof, and so these obviously are not decidable.
So if we look at line 108, it has several numbers.
Yeah, so the format of this is the first thing is the number of the step. The second thing is the steps that it relies on. The third thing is the name of the theorem, which is being applied at that step. And then we have the statement of it. So let's see if I can change some things. So I remove this step, now it's going to complain. Let me make this a little bit bigger. So I removed step 126, and then it complains, where is 126? So let's see. I can type the name of the theorem, and so if I just remove the 126, then actually it reproduced this here. Okay. Let's remove a little bit more so that it will have more difficulty reproducing here. Okay, so it produced a new step, called it D1, and now it's waiting for proof. It says the step is incomplete.
So just beforehand, so there is an automation that helps you to finish your
Yes.
proof?
Yes, so this does some simple proof search. So one of the things you can do is if all of the steps, so in this case, the reason why it was able to finish the proof in this case is because steps 121 and 125 were already written down, and so it was able to figure out with no information, I see 121 and I see 125, and I found this theorem, SIL5 IBR, which happens to prove exactly the statement that I want. So actually, the automation is sufficient that I could remove, if I left just the statements of all the theorems and moved every single other thing on that left column, then it would be able to reprove the whole theorem, which is an interesting.
So it can actually prove the final statement automatically without the 100 or so lines.
So you would have to, if you gave it all of the right-hand side information and moved everything on the left column.
Right-hand side, okay.
Yeah, so if you gave it all the steps of the theorem, but not the names of the theorems that you're applying, then it can reconstruct what names are being applied and to which previous steps.
Okay.
So, and also the other way around, right? We can also remove the right hand side and then just from the steps.
Indeed you can. Yeah, so I can, if I remove some of these steps, it just puts them back.
So in creating this document, how much do you have to type?
Um,
How much is?
So, if you know the library well, meaning that you can say positive and entry and all these, then you can type the left-hand column. You can type about half of the left-hand column, and it'll reproduce everything else. The reason I say half is because there's also a few, just like this. So this theorem here is proving if z equals a, then z is less than b implies b minus z is an n, if and only if a minus b. And so this is the same thing. So this is a substitution theorem. So these come up all the time in MetaMath proofs because it doesn't have a built-in mechanism for doing substitution of set variables for class variables. But this is, of course, easily derivable. And if I remove all of this proof, it will put it back. So it derives which equality theorems to find, and this also works on things like closure and some kinds of arithmetic with variables. There is a complete decision procedure for arithmetic on numbers. So you just so these are all implemented within this proof assistant has varieties of automations for doing these localized sorts of proof techniques. But I mean, personally, it comes with its own. This is written in Java, and it has its own text editor, and I tried to make syntax highlighting, and it slowed it down unbearably, and so I took it out. I would very much prefer for this to be a plug-in to an existing editor, but you know, my manpower is limited.
Talk to Macarius.
Yeah. I'm not. Writing IDEs is not my favorite activity. Let's just say. So,
When you gave a number of 30,000,
Mhm.
is 30,000 what? 30,000 of these proofs or 30,000 of these proof lines?
no, 30,000 proofs. Okay, so these are going through the different theorems. Okay, these are all very boring. Let's see.
Generate 40,000 meters.
Oh,
These are theorems about primes. Let's, okay, so this is some examples of the minimum 100 theorems. Let's see, what's something interesting. This was proven recently. Let's see. So this is the formula for n factorial. So this is the HTML output, and it's a little bit better in Unicode. So this is basically just exactly what we saw in the proof assistant, and only now they're being rendered in a more sane way. And let's see if we can see some nearby theorems. So, I mean, there are, so this is a bunch of,
You go too fast.
so let's see. We can go to random place in the file, read about Hausdorff topologies, I guess. But yeah, there are literally 30,000 of these theorems, and we have pages and pages of this.
So when you have this proof assistant which does things for you like this arithmetical procedure,
Yeah.
is it like what's the implementation like? There are people doing LCF here, there are people doing ACL2, like PVS not doing any LCF. Like, is it like ad hoc, or does it have some sort of proof technology behind it, or?
I guess it depends on what you mean by technology. It's probably on the ad hoc side.
Oh.
I mean, what I implemented was something along the lines of, when you see a certain kind of theorem, try a certain kind of proof method. So you see something that involves a bunch of integers, you have a method for detecting when something looks like that. And then when that gets triggered, okay, apply equality, or apply addition rule here. And then it just, based on the forms of the theorems, it just keeps applying. And then it sort of works its way backwards until it gets somewhere, or it doesn't. If it starts to work, and then it proves some things, and then it gets stuck somewhere, it will actually give you back the proof at the point where it got stuck. So I know that differs between some systems, whether they'll just give up entirely and not do anything, or do the partial proof, which might be going in an entirely wrong direction. Yeah, the way it's implemented now, it will do as much as it can, and then give you back the.
So it's not like a technical proof where you could say do the arithmetical reasoning now, or it just tries to do as much as it sees, and then.
Yeah, right now it's just there's a do everything button, and it just tries all of its methods. And yeah, I mean, I definitely like the tactic framework approach, which I've seen in Lean and such. And I've been thinking about methods for implementing that here, but this is a big project, to say the least. And I'm trying to work with this new. So there's a new proof assistant called SMM, which is being developed in Rust, which will hopefully be able to address some of the issues in the MMJ2 proof assistant. But right now it's very powerful, relatively speaking, and so it's kind of difficult to get away from it. But I want to see whether we can try something new.
Okay. Oh, I think we should give the floor to Bohua. Thanks.
which one do I?
There's HDMI and EGA.
Oh, okay.
This is HDMI.
Let's let the computer start.
You just missed my command. But you can still ask a question.
You're late.
Okay, so yeah, so these are still on two different screens. Can I get it on the same?
You can say various screens in Ubuntu in the settings. Yeah. Oh. Displays. Various displays.
Yeah.
Yeah. Apply. This configuration.
Haven't appeared yet.
Yeah. Sort of detecting cure.
Yeah.
Yeah.
Yeah, good. Thank you. So I have both have some slides and a demo. So let me just
Demo is better.
open up both. Yeah, so you will see. Let's see. So these are big. So the text is way too small here, so I should increase. Does this look okay?
Yeah.
Okay, but I'll show the slide first. Alright, so this is going to be a talk and a demo on Auto 2 and on the mathematics library using set theory in Isabelle 4. Okay, so this I think I've seen before. So this is a mathematics library based on Isabelle 4 and the CFC axioms. So currently we have in the library various assumes in set theory, group theory up to first isomorphism theorem analysis, construction of real numbers, topology, including the connectedness and the intermediate value theorem, algebraic topology going up to the construction of a monogroup and others like the Arrow's impossibility theorem. So there's total of 13,000 lines and more than 3,000 lines of ML code, and it takes 5 months of work so far to build up this library. So dealing with set theory, so there are several complexities of set theory compared to text theory that we have to manage, and we have 3 techniques currently for managing it. So first of all, this is the first one is the issue of hiding definitions. I think this is used in many other systems as well. So many concepts such as ordered pairs or natural numbers are represented as sets, but we basically never think of them as sets, except initially when trying to prove their basic properties. And the way we handle this is that we do it in the 3-step process. We first define the concept like ordered pairs. We add the definition as a rewrite rule to Auto 2. Then we prove the basic properties, add them as reasoning rules. And then the key part is that we delete the definition of the concept from Auto 2. So basically, after we are done with this, Auto 2 doesn't really know what ordered pairs are how ordered pairs are represented. So it will never try to expand the non-intuitive definition. Instead, it will just use the basic properties that we are familiar with about ordered pairs. So this is applied this is applied everywhere, and we'll see examples in the demo. Properties, so there are concepts like group, so each group, each ring, each lattice, which are usually declared as type classes in Isabelle 4 or similar systems. they are represented as predicates in Isabelle form, and there may be extensive dependency graphs on such predicates. And this is actually the example that I'm going to show. And in Auto 2, we register this predicate as property. So during the proof, Auto 2, during the proof, it will store a table of known properties about existing terms, so terms that appear in the proof, and we automatically propagate dependencies such as this. The third technique we use is the concept of well-formed terms. So in set theory, since there's no types, so it's easy to form terms that are meaningless according to a human. And so we define a concept of well-formed terms for use in automation only. So this is emphasized. So I'm making no change whatsoever to the logic. So this is not a concept in logic foundation, but it is only used in the automation. So examples. So some of these are similar to type constraints. For example, A plus B, both A and B has to be in this structure. So these are like type constraints. But this well-formed condition is also more general than the usual type constraint that we have. So for example, taking the inverse, we can set the condition that A has to be a unit, or taking a quotient group, we can set the condition that H is actually a normal subgroup of G. Okay, and in Auto 2 we can register conditions like this as well-formedness conditions, and during the proof we maintain a table of well-formedness conditions. And so basically Auto 2 can sort of manage these conditions in a table. Okay, so that is basically the 3 slides that I have. And now I will start the demo because I thought this is mainly about the demo. Okay, so let me open up this I just did last evening. So this is sort of just a look of what happens when you try to develop something new in Auto 2. Okay, so a lattice. Well, there are 2 approaches to defining a lattice. First, one approach is to define it as an algebra as a set containing the drawing and mint operators. Another very common approach is to start from partial order, and a lattice is basically a partial order satisfying some additional properties. In particular, a lattice is both a drawing semi-lattice and a mint semi-lattice. So a drawing semi-lattice is an order satisfying this condition. So for every x and y, there exists least upper bound of x and y. Does this make sense? Yeah. Once we define this, so this is adding this predicate as a property. Okay, so this line just adds this as a property. And now we prove 2 lemmas that on how to use the drawing semi-lattice property. So the first one is very obvious. Drawing semi-lattice implies this is an order, and it certainly can be proved by Auto 2. And then we add this is a forward bootstrap, which essentially adds this as a property propagation rule. Okay, so this is added as a propagation rule. In the next part is the trickier one. So for every x and y, we should be able to obtain this c, which is their least upper bound, and we can prove this automatically. Okay, and now notice here we add this as a backward reasoning rule. And what this means is that we add this reasoning rule such that this theorem will be applied in Auto 2 only if we want this conclusion. That is, only if we want to get some z satisfying this condition. Now, so this is important. So if we add this as a forward reasoning rule, for example, then what will happen is that, so you can see the effect here. So you can see the effect here. So basically what happens is that the system will, for any R that is a drawing semi-lattice, and for any 2 variables that are known to be in R, for any 2 terms that are known to be in R, it will produce this least upper bound of those 2 terms, and that will be disastrous. That will fill up the search tree very, very quickly. Okay, so that is why we definitely should not add this as forward reasoning and instead as a backward reasoning rule. Okay, and then we delete the forward part of this rewrite rule. So because this is already covered by these two lemmas. Okay. So so the effect of this line, basically we define semi-lattice and we we specified how to use the semi-lattice property. And
at which place do you do the deleting operation?
Here. So this line we can define a better function for that, but right now this is how we do it. So this deletes this step. But yeah, there can be better syntax for it, but right now this is.
Well, it's not a problem of syntax. So you have a very strict time order in your document.
Yeah, time order in the document. That's correct. Yeah, yeah. So I mean, most of the time we only need to add or delete the theorem once. So we add this rule here, and then we delete it here. So usually it's pretty clear. Like it's basically this theorem is applied in this block, and it will never be applied again. So there is definitely time order in this document. Yeah. And now we can prove that in fact there is a unique list upper bound. So we just asserted that there exists a list upper bound. Now we can prove there is a unique list upper bound. So for human, even for human, you have to think a little bit about it, but it can be handled automatically. Okay. So now we prove that the list upper bound is unique. We can define it as this expression, which is the drawing, and this is the Z operator, which just chooses the unique element satisfying this property. So this is the drawing of x and y, and we define syntax to be like this. So this corresponds to this symbol in the textbooks.
So
okay.
The question is, so is the part of Isabelle Foll, or?
I believe is part of. Oh, sorry. This is part of. This has to be defined using ZF axioms. This has to be defined from ZF axioms. But it's a very basic choice operator. So it's not. There's another choice for when you have just have existence. For your unique existence, you can define this operator. Okay. Any other question? Okay, and here this line we register. So we note that the drawing function for the drawing of x and y has to be in the structure R. So we specify the well-formed data like so. So this in dot means y is in the carrier set of R. Remember, R is a structure, is an partial order. Okay. So again, we prove the main properties of drawing. So notice that this condition drawing semi-lattice, which means there actually exists a unique drawing, and so that means this actually works, and this will work. So if I just have order here, this will not prove it, and in fact this theorem is false. It's just false because this statement is a unique existence choice, but it's not even unique. There isn't a unique existence. So we have to have this condition. And we add this rule to be applied whenever we have this term.
Excuse me.
Yeah.
I was blocked on the previous explanation.
Yeah.
When you registered the waveform data,
Yeah.
you don't impose that R is a joint semi-lattice, or you do?
Impose what? R is
That R is a joint semi-lattice?
I can impose it, but I don't.
In that case, you don't do it.
In this case, I don't do it, but there's a choice to be made, and it's not necessary here. But I think it won't break anything if I impose it.
Okay, well, don't break your demo.
Yeah.
Well, what happens if something is provable but not by auto 2?
If it's provable but not by auto 2.
Yeah, what do you do then?
I believe so what do you mean? So this, if it's provable, it has to be proved by applying previous lemmas.
Yeah.
So here's a
right?
proof language. You might want to show the richer proof language, which you have, like these lets and halves.
Oh yeah.
That's all I meant. Really.
Yeah. Oh, I'll show that later. Yeah, I'll show that later. Yeah. So you also see the effect of declaring the properties and well-formed terms here. So I said that this theorem will be applied whenever this term appears, right? So you see the record here. So this is a property and these two are well-formed conditions. So basically, when we are applying this rule, we are only matching the term x drawing y. Okay, we are only matching x drawing y, and these three conditions are sort of the side conditions that will be checked later after we found this term x drawing y. Does that make sense? Okay, and that is also why I don't need to add drawing similarities as a well-formed rule, because it is already a property. So whenever something can be added as a property, I don't need to add it as a well-formed rule. But the data is getting into details, I think. Okay, so we add this as a rule. Okay, and likewise, this is another rule that can be proved automatically. So this is the other property of drawing, and we add it as a backward reasoning rule, meaning that whenever we want to prove c is greater than or equal to x drawing y, then we have to prove these two sub-goals, basically. Okay, and it is shown here. So whenever we have this goal, we get this goal, this conjunctive goal. Okay, so the third property of drawing is when we want to show that the drawing of x and y is equal to something, then we have to show these two conditions. So c has to be greater than both x and y, and for anything greater than equal to x and y, it has to be greater than equal to c. So these are the three basic properties of drawing. And once we proved these three basic properties, we delete the definition of drawing. So from now on in the proof, we will no longer expand the definition of drawing as this choice operator, but instead we will only use these three properties. Okay, so basically we will never see this, appearing for drawing again. We will never see this symbol appearing again. Okay, and now we have these basic rules. And so this is showing the logical ability of Auto 2. So this can all be proved automatically. Okay, this if you give it to human can easily prove it, but it requires many steps. So all these equalities is actually by appealing to this drawing I, so it expands to three sub-goals and so on. And so there is a certain difficulty in it, but certainly Auto 2 can handle this pretty well. Okay, so this is the drawing, and okay, so the upshot is that we define the drawing similarities property as a property. We define the drawing as an operation, and we prove its basic properties. And we can do the exact same thing for meet, which is the opposite. Okay. Okay, and idempotency, commutativity, associativity. I should mention here that I added, so you'll notice that I added commutativity and associativity as rewrite rules. And I should say that adding commutativity and associativity as rewrite rules is not a good idea. Yes. Instead, these are sort of, we know that drawing is an AC function for if this is a meet similarities or drawing similarities, and we should use special rules for dealing with AC functions. So right now, use special rules for AC functions instead. So this is the to-do. Okay. Yeah. So right now, yeah.
Do you mean you have these rules somewhere?
Right now, I have written things about associativity. So right now, I can explain what I currently have. I can have this function here. Yeah, I can just give an example here. So here we have the associativity of the composition of functions, right? Is that okay? This is the composition of functions.
Yeah, but there's no commutativity.
Yeah. I'm just showing if you have associativity only, I have this rule for it. So instead of adding this as a rewrite rule, I add this as our associative proof stack. So basically, what this rule does is that whenever it finds two terms in the proof that are equal up to associativity, then this rule will make them equal. This rule will declare them to be equal. So for example, after I write this, so this will take some time, but I think it worth it. So so I have to kill all this. I think I have enough time. Okay. Okay. D equals source of y. So this may be something to be improved on because I have to specify all these conditions. So now I can type all sorts of things. So let's see which order should I. So I think it's yeah. So what's going on? Here?
Target W equals source Z.
Yeah, so it goes in, basically it can be done in one step instead of applying all those associativity rules. Okay. Okay, so now I've destroyed the state and it will go back again. But so let me just say, so currently I added this as a rewrite root, and I will show that for simple statements, Auto2 is able to deal with this, but this is not a sustainable solution. I should have something similar to functions there. Okay, so a lattice is something that is both a drawing lattice and a means lattice, so that is obvious. So then there are these absorption properties as is stated in the book. So there are these absorption laws, and this can be proved automatically. We have to wait for this to come back. Okay, and now this distributive lattice. So distributive lattice is here. So let's read this while this is running. So the most thoroughly studied case of lattices are distributive lattices and modular lattices. A distributive lattice is a lattice satisfying either and hence both of the distributive laws. And so basically we have to show that these two are actually equivalent. Is this clear on the screen? Okay, yeah. So we defined the distributive lattice using the first rule. So we used this rule to define the distributive lattice. Okay, so this is a lattice, and this satisfies this rule, and we delete the forward case of this rewrite rule as before. Okay, so now we want to prove the other rule, right? So we want to prove the other rule, which is this one. And so Auto2 cannot prove this automatically. Okay, so well, for some good reason, because the proof is this 8-line equality calculation. Okay, and these 8 lines, the most this will be difficult for human, even for human to do, because it involves 2 very tricky operations, which is replace x by this term here, which is using absorption. This is the first one, and then these are obvious, and then replace x by this one here, again using absorption. So there are these 2 very tricky operations that we do. So now I did demonstrate the proof script. Okay, yeah. So I say that x squared okay, so it can prove the first expression, obviously, because it knows the absorption rule. And then, I mean, I can list all 8 equations, and maybe I define some sort of syntax for listing in this form. But I mean, it turns out I tried this at home, so I only need to list 2 of these expressions.
So when you said have, it automatically invokes Auto2 on proving.
So what is the question? So when I invoke have, yeah.
When you stated the first half, it automatically invokes Auto2.
Yes, yeah, it invokes Auto2 to prove it on the assumptions, and then once it is proved, this fact is added for use for all the future invocations of Auto2.
I'm just wondering why sometimes you have to write by Auto2 and sometimes you don't have to. So it's implicitly used.
Yeah, it's implicit. Yeah. So this funny half. So this ampersand half are defined by myself. So I just call in this ampersand half, it just directly calls auto 2. So I just define this myself. So actually, this auto syntax is just done over the weekend, over the previous weekend. So let's see. So this is X. So this is almost done. Okay, so this has 2 halves, and we can QED. So this will finish in about, if I got this right, this has finished. This is finished in less 3 or so seconds. So this is sort of testing the rewriting ability. So this is a congruent closure that is inside auto 2, and this is testing this. So the congruent closure is now actually pretty fast. So we can do all this using both commutativity and associativity, as well as this rule in 3 seconds. Although, as I said, in the long run, we should not have add commutativity and associativity as rewrite rules. Then this would go faster. Okay. So in any case, so this is
I mean, there is, as it were, something to be said for what was written in the textbook, and I guess if you wanted to, you could write that, couldn't you?
Sorry, I can write all 8 lines.
Yes, I mean, if you want, you know.
Yeah, I can. And
from a didactic point of view, it's more illuminating than.
And I think it will also go faster, especially if I don't have commutativity and associativity as rewrite rule. Good.
Only the demo is slower because you have to type.
The demo will go slower.
And do you have a calc syntax, something that doesn't force you to repeat the left-hand side?
Right. That is in calc and in Lean. I think it's defined in Lean. I don't know if it's in calc yet, but that's a to-do list on the to-do list. And your question,
I mean, when you explain the proof, you see it's simply the absorption that is needed. So could you put only the absorption, the equality that x is equal to, because the right part are the same. So could you,
Good. Yeah, but I guess it's written in book like this, so I just But both way works. Okay, so in the book it continues. Actually, every lattice satisfies both of the inequalities, this and this. To see this, blah blah blah, and I don't need to read this. So these are the 2 inequalities, and auto are able to prove it on its own. So I don't need
to see this we call auto 2.
Okay, good. So this is with the book. So now I want to show that certain things that are actually lattices, right? Because that is if we want to apply theory of lattices, we have to know these things. So this is the subset ordering on the power set of S. So that is basically the prototypical example of lattice. So auto 2 cannot prove it. Okay, so this is a live demo. So I mean I tried this before, but I think it will work.
What is S?
S is an arbitrary set. S is an arbitrary set. Then we take the power set of S. Then we take the subset ordering on the power set.
So how does it figure out at this point that S is an arbitrary set?
So a power function is a function from set to sets. So actually Isabel has this typing, so it figures out that S is of a type of set.
So you have some simple typing imported from Isabel Fall or Isabel Pure?
So let's see, there's typing in here. So Isabel 4 has this set. This is first order logic and type theory. There are basically 2 elementary types. These are I and O. So I means type, I means sets, and O means propositions. So you see that drawing semi-lattice is defined as a function from I to O. So that means it's a predicate. It takes a set to a proposition. And the power is defined as I to I. So it takes a set to a set. So there is a basic, very elementary type checking going on here. So here we know that since this is S is, so power is applied to S, so we know that S is a set, is of type I.
How do you know S is quantified universally and not this type?
quantified universally.
Yes, how do you know
So
where S
every-
comes from? Do you have some pre-declared?
Yeah, the
pre-declaration
higher up the
somewhere?
buffer, you'd already decided what X was.
As
see
so
what I
you
And then
mean
by mistake you used the wrong letter.
so you can define constants. I don't know how this works. So does anyone know how to define constants?
CONTS.
No. Oh,
Yeah.
constants. And then what? Okay, I. Okay. So now let's remove this. So now S is a constant, and so it's sort of black now. That is the effect. And then if I remove this, S is blue. So blue means it's a free variable, and all free variables are in the theorems are quantified. Okay. Okay, so we can. Okay, so first of all, we should let, let's say, R equals subset. So we can define new variables here. So this is just defining R, and we can just for sanity check, we can show that R is an order. So this is already proved. And now we want to show that R is a drawing semi-lattice. Okay, so this red line here means that auto 2 is not able to prove it. So we need to go deeper, and go deeper we have to go to the definition here, and to save time here I just do copy. So again, this is something that can be improved. Maybe we can have a button that automatically produces this. So again, it's not able to show it. So it needs this Z, right? And so the problem is that auto 2 doesn't know what to put in for Z. Okay, and well, human knows it. We just take Z to be the union of X and Y, right? So we have, so one way to achieve this is that we take union of X, Y is greater than X. So basically we verify the, what's going on here?
Need a with keyword.
Yes, yeah. I don't know the syntax now. Yeah. Okay, good. So all three lines finish, and so this is a very good news. So this end here completes means it can show this for all, and so now we can. So this end also completes. Okay, so now it has already shown that R is a semi-lattice, and we just have a similar code for meet. We just reverse all the. This is our intersection, and it finishes the proof. So there is a theorem here, so now it finishes the proof. And you can also see from the printout here, this is question mark S, which is an arbitrary variable, so this shows that it's quantified over S. Okay, so this is basically the syntax. This is auto 2's proof script syntax. So basically it just consists entirely of the mathematical statement. So I think this is better, easier for mathematicians to understand. So here there's a sanity check, but I don't really need it, so I just remove it and allow it to run again, so it finishes.
Why do you need the definition? Can you remove it and simply give a hint?
Give a hint.
This line I agree, but why have to repeat the definition of Johnson?
Yeah. So I mean, so right now in practically, when I give a hint here, I need the variable X and Y, and so I need to retrieve X and Y here. So I mean, there are various ways I think to change the syntax to.
But it's a bit strange that your the X and Y is used outside of the scope of the universal quantification.
Oh.
Yeah,
So
they're not
this,
really the same X and Y.
so actually, let me explain this. So basically,
One's green, of course. And the other's blue.
so there's a trick I did here, which may not be the good idea, but that's the trick. The trick is that whenever you have this half expression, these bound variables have to be new variables, and these variables are instantiated within the half block. So if I change this to y prime.
This will fail.
This would fail because this y is not recognized.
How do we know it failed?
Well, this is the red line here.
It's got the little.
It's underlined.
Yeah, it's the red line here, and this, yeah,
I
all
didn't
this.
notice all this.
Yeah. So I need to change this to y prime. So these two variables which are appear in the for expressions are they have to be new, and they are essential. They are taken to be variables inside the half block. So that's a trick I did, but I mean people may have better suggestions on how to do this.
It's funny. It still looks as though it's slightly underlined. Or is that just an artifact of the
This
of the rendering? Or
this gray underline means it succeeded, and if you click on this line, you can see the proof. Yeah. Yeah. So the gray underline are healthy. Red underline are healthy.
Okay. Can you say a bit more about
Red is
the
not healthy in gray.
type system?
Yeah.
Can you so basically because it's a theory, you can apply any function to any object, but these properties which you have used to automate your typing will prevent you from doing anything important. So I don't know if you have a plus function, for example, you could apply it to arbitrary sets.
Yes. So I can. So I think I can explain this to So for example, I have this plus function, right? So this is not on natural numbers. So this is a plus function on natural numbers, and so there's absolutely no restrictions on what is the. So it's the left and right side can be arbitrary sets. They don't have to be natural numbers. So if I just remove this condition, there will not be any. There will not be. So the Isabel will recognize this as a valid expression, but this obviously cannot be proved by auto 2. So you have to have this condition here for it to be proved by auto 2. So likewise, for all these theorems, so the associativity, which is proved by induction, so this is the syntax for induction. I believe I have the new syntax which also works. So it's induct, the same to. Okay, so this is the new syntax for induction. So you see, so for example, the associativity theorem is guarded by these three conditions. So basically, you can construct x plus y on natural numbers, where x and y are not known to be natural numbers. But because all those theorems that are dealing with x plus y are guarded by these conditions, basically you cannot prove anything about that term. So that is sort of how we unofficially maintain type in this system.
And some of the conditions can be registered as the properties.
Yes.
And some of them don't have to, right?
Some of them can be registered as properties, some of them can be registered as well-formedness conditions.
Oh.
So for example, in this expression, all three of them are well-formedness conditions. Because the first two are well-formedness conditions of this term, and Z is the well-formedness condition of this term as a whole. So it appears on the right side of this. So if I go to the end of the proof, so you see that this is the rewrite rule, and all these three are well-formedness conditions. So this, and we only have to match this term. So basically, how this rule is applied is we match this term, and then we check these three well-formedness conditions in the table of these conditions.
Can you deal with arithmetic?
Basic arithmetic. I mean, so there are various things that are added. So for example, let me just show this. Okay, so this would work. So if it's a ring, if R is a commutative ring, okay. Let's see, okay. Okay, I'm not very super confident about this, but let's try. Okay, so you see what it can do and what is bad at. So it can expand this out. But if I replace it with 2 here, maybe. Okay, this is good. Okay, so these 2 as an element of R and 2 as a natural number. So before I put in 2 as a natural number, which don't make sense at all. Okay, so this is algebra. Okay, so natural number arithmetic. There are various rules. There are various things that I need to implement, but you can see that algebra simplification is very important.
Okay.
Yes. Okay, so but I think so. There are a bit more proofs, but I want to show. But this I need to add more things. So this is showing that this is a distributive lattice, and it actually shows that this problem, which is that we have to define the drawing eval. So if this is sorry, this is subset order. What I'm thinking. R is in a subset. Okay. So basically, the problem is So last night when I tried this proof, when I want to show that the subset order is a distributive lattice, because that's a very important property, it is unable to show it. And the reason is that even though we proved this ordering is a lattice, we haven't shown what is. There is an explicit theorems about what is drawing and meet evaluates to, even though it's sort of stated in the proof, but it's not explicitly stated. So when I explicitly stated that, it will know to apply these rewrite rules and show that this is a distributive lattice, and so on and so forth. So I also have examples for product, but I think this is enough for now. Yeah.
Wait, so in that previous proof where you showed the rewrite rules, is it observing the previous proof in order to figure out that expression, or?
You mean here?
Well, I mean the fact that you put in the union and intersection.
This proof.
So it's not looking at the previous proof of the lattice where you use those.
No, it's not. Yeah.
So it's just proving those same theorems again?
Yeah, this theorem. So it's not looking inside the proof. The reason it is able to prove this automatically because I already gave the candidate for drawing. So you see in the previous proof when I gave the explicit candidate for drawing, it is able to finish. So here again, I gave the explicit candidate for drawing, and so that's why it is able to finish. But it's not looking inside here.
So then would you be able to prove all 3 of these theorems at once?
The to-do list and the to-do list. so there are maybe ways to make it happen. Yeah, thank you.
More
Okay,
questions?
that all?
Thanks. I can do something like switch it on and switch it off.
Bohua,
Yeah, yeah.
what is the hardest theorem that you have proved? What is the one you consider your flagship?
Maybe the hardest, maybe the completeness of real numbers according using the Cauchy sequences.
Yeah.
To restart the machine. Not sure what to do right now. I can restart it, but I can also just talk. Oh, maybe can I borrow one of your notebooks just to show some things which will not be very demolish, but seems this is failing for some strange reason.
Have you tried VGA?
The issue is that I don't have VGA here because it already worked before with HDMI. But like Linux is Linux. Just do you have a browser connected to internet?
Yeah.
Okay, well this would be enough. Just give me a browser window.
Yeah, we need to do. You want mirroring, right?
Sorry.
You wanted the screen.
Yeah.
Mirroring as well. So yeah.
That
Oh, it's already mirrored.
it's sometimes it's too clever.
But maybe I need to log in.
Uh-huh.
So this is
The super demo effect.
super annoying thing.
Yeah, that seems working. It might need just HTTP because if you do HTTPS, it might not be giving you the.
It works every time in the office, but it just takes some time in my office.
Well, maybe I should restart my machine.
You want me to go get mine? It worked this morning.
Like, do you think it will start working or not really?
I think you can try other ways. Yeah. Maybe
Are you connected to
Yeah.
internet?
What are we doing?
Just the browser connected to internet. Yeah. Okay. Can you borrow it?
Oh, okay.
Okay. It worked. You stick it.
And
It seems very slow.
yeah. Okay, great.
We'll So what I wanted to show you was a demo. We did this. We did this course recently in Prague, showing for-proof assistance on this informal proof of Canton Bernstein. So it says that what does it mean for a function phi to be monotone with respect to inclusion, and what does it mean to be anti-monotone, and you sort of do this basic set theoretical definitions. Then we proved Strelitsky. And then we proved Canton Bernstein using Strelitsky, using this sort of relational way, like instead of having two functions, one going there and the other going back, you have this relation which is sort of the functional properties. So we did this as an exercise in for-proof assistance in Isaac, Isabel, Holite, and Koch. And it was a lot of fun. At some point we dragged John Harrison and told him to formalize it in Holite, and he did it like under 1 hour. So I wanted to show you because that was something which I recently did in Isaac. And I'm normally not really a Mizar user, neither a developer these days. But I can probably show you the raw Mizar file here. So that's this thing. And I can show you the hyperlinked version, which is this thing. And on that I wanted to explain what Mizar is basically. It has this horrible importing part where you specify how to import, for example, theorems and I don't know, definitions and all these weird other things from the Mizar library, which is like a big library containing something like 1,000 articles. So that's definitely a very bad part of Mizar because you shouldn't be knowing the library in such a detail. You should say something like in whole, like import main, right, or something like that. So once you are done with that, you reserve variables with their types. So Mizar is a set theory. It uses Tarski Grothendieck, so it's like Thermal Frankel plus universes plus the Tarski's axiom A. And on top of that, it has these soft types, which you have seen in the previous two talks, specifically in Bohua's talk. The thing which Bohua talks properties would be called source of types in Mizar. So set, everything is set in Mizar. But for example, function of Bohua is a dependent function, dependent type. So Bohua is a power set of A, Bool B is the power set of B. So F is now a function going from the power set of A to the power set of B. And so that's, if I start clicking now, it will show you how these things are defined. So for example, this Bool is really just power set, like this is a redefinition, so on the rail thing.
It's nice, but don't click too much because it's hard to follow you.
Yeah. So this is just a set theoretical definition of power set, and I'm actually not sure why you define this macro, this defpred, so just forget about it. Maybe it's used later in the proof of existence and uniqueness. But basically, the definition is the result type of the power set of X is set, so that's like everything is a set, so this is trivial. And it means that for any set Z, Z is in this defined object, which is limited by it, and these are ephemeral with Z is a subset of X. So that's this trivial definition. And now you have to show that this really defines a function, so you have to show that such an object exists and that is unique. So that very likely, if I click on these things, like it will show you the desired proofs, etc. So that's the power set. And what is a function to show you the sort of typing mechanism? So the function is a sort of dependent soft type defined for any two sets as a quasi-total partial function of xy. So quasi-total means something like almost total, very likely, and partial function partial function is defined like this, so it's a function-like relation of xy. So again, let's have a look what is relation of xy. Relation of xy is something called a mode, again, which defines the self-typing, so it's something like your property. And these things, there's a Cartesian product of xy. So this says that relation of xy is any subset of the Cartesian product of xy. So that this is how we define the soft type. I could again click on this one. Now you will see that it's the element of the power set. So these are basically the dependent soft types. Function like, you can totally imagine what it means for a relation to be function like. So for any three objects, x, y1, y2, if you have x, y1 in x and x, y2 in x, then y1 equals y2. So it's a functional property.
And all x, y, and y are object?
So object is a new feature of the Mizar language, which I disagree with. As I said, I'm not really an important member of this community. And it's basically a set, but they wanted to introduce some extra automation for sets. So for example, set would be something like a collection of objects. Something similar to what Bohua was saying about expanding definitions. So for sets, you automatically expand some definitions. Objects are morally sets, but you do not automatically expand some definitions for them. So it's a sort of automation thinking. So this ATTR stands for attribute. So attributes are the major part of the sort of Mizar self-typing system. You use these attributes. All these attributes are morally predicates, so like function-like. The thing which you do with them is that you automate the sort of typing hierarchy, again, like you saw in Bohua's talk. So for example, once you have two attributes, you can say that one implies the other. So this gives you like a subtyping hierarchy. So any empty set is also function-like in the set theoretical definition. So you use the keyword cluster for saying this, and then you have to prove it. So if I click on this keyword coherence, then you will see the proof saying that if something is empty, that's also function-like. You also have like the thing which especially Frey-Guidek is very unhappy about is that the Mizar community wants their types to be non-empty. So each time you would want to quantify over a type, you first need to show that the type is non-empty. So that's done by this sort of registrations, again using the keyword cluster. So this one says that there exists a function-like relation, basically. And again, there is an existence proof attached to this. This one is again, so it's not called attribute, it's called a mode, but it's just a part of the sort of typing hierarchy. And in this case, it's really just a macro. So whenever you write a function, it expands things into this function relation-like thing. So that gives you a how to.
What does the for set mean?
I'm sorry.
For set.
Empty is a function like for set.
Yeah, this is the syntax telling you that this particular automation works for arbitrary sets. You could also say it for something more specific, for example, for relations or for matrices or etc. So this is the base type. This is the sort of antecedent of this sort of soft typing rule, and this is the consequent of the soft typing rule. And you really do a lot of stuff using this, and again, it's very similar to what Bohua.
So did you use that fact in showing that it's non-empty? You just say the empty set is a number?
Say it again.
In showing that the function like type was non-empty,
Which one?
in the thing that you just had about, you showed that.
No. I was saying two things. So I was saying that there exists an object which is function that is basically this, like this.
Yeah, an empty is such an object.
And every empty set is a function. So these are two things. This is stating the non-empty extension of the type function, and this one is stating that any object which is empty is also a function.
But the empty set is an instance of.
Yeah. That's just to show you how the types work in Mizar. So here to formalize the monotonicity which Czech has defined somewhere up here, we basically use exactly the syntax which he has here, and we say that like function of a monotone if for two subsets of A, use sort of phi implies for phi subset of phi. These Mizar is mostly ASCII. They used to have some weird high ASCII symbols long time ago, but then everybody was unhappy with, like, this was before Unicode, so they removed them. They ended up with this sort of.
So this means subset?
Yeah. That's like they somewhere around 2000 they consistently that they had these fancy high ASCII DOS characters before 2000, but then they ported things to Linux and things broke completely. So they were very unhappy because, for example, in high ASCII you have the membership symbol, and now they have to use what should I say? So after all these definitions, you get some sort of definitional theorem, which in this case looks like this for monotonicity, which is sort of obvious, like for any two sets A, B, for any function f of the vector k type, f is monotone if and only if. So this is a theorem to which you can refer at any point, and the same for the anti-monotonicity. And then you get you can write your theorems, right? So I got these theorems for free. Like I was following Chet's PDFs, so I just wrote them anyway. But these are all for free. This one is, I think, image under a function. So it's in general defined for relations thing, but an image of a set under a relation. The range. So this is a longer proof. In Isar, I should show you how it's written originally because the HTML isn't totally faithful. So it's this sort of natural reduction style called Fitch in the US. It's been actually invented by Jaškovský in 1920, not 1927 or something like that. So and actually the Mizar guys thought for some time that it's their own creation after somebody told them that it has been invented by Jaškovský in the 1920s. So you probably all know it from Isar today, and also like biblical people started to use declarative style at some point. So it actually is slightly different from Isar, in the sense that in Isar, the thing you are proving is fixed. It never changes during the natural reduction proof, and only in the end, like the thesis is assembled in the end of the Isar proof and compared, like the thing which is assembled from the proof is compared with the thing which you stated in the beginning. In Isar, it's watched from the very beginning, and when you do these steps like assume and let, it's compared with the current thesis, and it has to sort of structurally match the current thesis. So you can only do an assume step when the thing which you are assuming here is actually a real assumption in this statement. And after that, the thesis which you are proving is modified, and again, you can only chop off an assumption if it's in the remaining thesis. So you can see this in the HTML. Like this is the thesis after. Oh, is it here? So after the let step, like for AB being set, disappears, and you are left with the part saying for F being function of AB, blah blah blah. And after all, like it's basically like some sort of straight pattern in whole light, for example. So this thesis is changing during the proof until it becomes true, basically. And the sort of similar part to like auto 2 is called by in Isar. So that's this sort of obviousness tactic on which like the Mizar people have been working for a very, very long time, like trying to figure out like how hard and how easy should be the steps. So when you say like statement blah follows by some previous theorem and by some local lemma, it actually does a lot of stuff. So it does sort of full dependently typed congruence closure over all previous constants in your sort of universal discourse. So if you have some equalities here, like imagine you would have here something like U equals V, for example, then those two things would be merged during the proof checking process. it does full hierarchy climbing. So whenever you sort of merge two things, it also merges their types. So the equality is sort of extensional set theoretical equality, and the two things can actually be having different soft types in these eyes. So one of them, for example, can be a natural number, the other one can be a real number. And now when you say these two things are theoretically equal, then you basically start merging all of their properties and propagating all the type checking rules which you have about them. And then it does some very limited sort of refutational theorem proving all these congruence classes. So it doesn't do like full resolution style theorem proving. It does very limited amount of unification. Basically, it does some sort of one-way matching when you.
How much does it instantiate universal
Yeah.
equalities when it computes the congruence classes?
For example, so the congruence classes they become constants. They become your sort of Herbrand universe basically. So at some point after you have done the congruence closure, your proof checker or your automated theorem prover in design works with these constants, and it totally forgets about the fact that they come from some previous, possibly multiple things in your previous Herbrand universe. So that's sort of the Herbrand universe you are working with, and this is used to instantiate the general statements like these quantified guys together with the local amounts here like this A1. So this it's funny that I don't see it here. This universal statement like which is saying for xy being set for r being relations, so that x subset y holds r of x is subset of r of y, would be at this point matched against this. Oops. Against this A1 and against this this sort of conjecture you are proving, and it wouldn't try to match further against some universally quantified for now. So it wouldn't do a full resolution. It would only do some sort of one-way matching with things which are already. So that's the Martin Davis thing from 1960s claiming this is what humans might consider being obvious.
So what does the double column thesis mean? Always happens.
This is after comments. So the like everything after double column is a comment.
So what? Okay.
And
the general thesis will be that.
So the thing which is buggy is that on my screen when I hover over a thesis, it shows it to me what the thesis is. Whereas in order to show it to you, I have to click, and even then it doesn't show it. Oh no, now it shows. So this is just a thing in the HTML to show to people some additional information about
what is
what they are doing.
What is the current goal is? Oh, okay.
So you don't see it in your current design development.
So the HTML is produced after the proof has been verified.
The HTML can be produced anytime. So
no, but the one with the hover information.
I'm sorry.
The HTML with the hover information.
Yeah, that can like I do not have Emacs here, but
Don't
but basically one way how to show it to you is like just to copy something from here. Sorry, now I don't know how to stop it.
Yeah, you can control it, select everything.
So basically, what happens when you are developing things in Emacs is that you have like one keyboard shortcut telling it now display it in browser with all the clickable information, etc. And then you have also like these things for calling the sort of automated theorem provers on. So that's sort of accessible from the Emacs, when the thing which sort of disambiguates the stuff to HTML, etc. I'm not sure what happened here right now. So when at least like I do not formalize Mizar these days. Like last article I wrote like 15 years ago, but I did this CBS this cartoon Bernstein thing for the course, for example. So the way I do it is constantly have like things like Z3, Z0, and the more complicated proofs found by me by writing this by, then semicolon, that calls sort of the Mizar sledgehammer for me, which automatically finds by sending it to my server and to all my machine learning, blah, 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 that I should be using Z3 and Z0 here, so I can show you my own.
So that's your environment.
So the Emacs thing I wrote like 15 years ago, and they are mostly using it the sort of HTMLization and the sort of automated theorem proving capabilities. I don't know how many people are using it. Like yeah, like so. I don't know what else. So this is sort of the natural deduction which has been like known to anybody using Isabel recently. The soft typing system, I told you what it is. The foundations are set theory plus this Grothendieck universes. You have these things, these reconsiders. So that basically, because you are really working in set theory, as I said, you can always show by proving that something has some differences of type. So for example, at this point, y0 is probably only a set, and by the keyword reconsider, you define another local constant in the current proof called y1, which has a particular type, in this case subset family of A. And sometimes you have to prove this in a sort of difficult way, sometimes it's very easy. But that gives you a way how to sort of steer the soft typing system, because some things go with one soft type, some things go with another soft type. And then this sort of equality is used in the congruence closure algorithm to merge all the types all together and do stuff with them. Yeah.
So you have to give it a different name when you do this reconsider?
Oh, you don't have to, but if you don't, then the old one is shadowed by the new one. So it's more, it's smarter to keep both in case you need the old one. So that's the sort of way how you steer the subtypes. And there are also some other ways how you can do it. Like sometimes you can sort of do some sort of casting operations. You see if there is some other interesting command. Yeah, so this defunc. So because it's basically first order set theory, sometimes you want to do slightly higher order things like scheme of replacements, scheme of induction. So they have these defunc commands, which locally allow you to introduce basically a second order constant here, local constant in the current proof. And it uses this dollar notation, so it's like a lambda expression saying like lambda $1 blah 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 f of $1 equals this, plus you have to state the type of the arguments here. So that's sort of showing you that Mizar actually goes. They call it like not first order logic, but for the 1.1 order logic or something like that. I might be able to show you these things which are called schemes in Mizar. Just think where it could be. This might be a reasonable. Yeah, there are some lambdas here. Yeah. So this is compared to what you get, for example, in the whole logic, a slightly painful thing in Mizar, which probably could be automated better, but currently it isn't. So in order to switch from a function, in this case this f3, which takes one object argument and returns an object argument, and this is a meta function. This is something like, for example, a successor on ordinals. So it can be an object which doesn't live in the set theoretical universe, which is not a set. And you might want to create a set theoretical function from it, so something which is really a graph in your set universe. So this says, provided that for every object which is in this probably domain set, right, holds that the function f3 applied to the object is in the range set, you can really create a set, an object in the set theoretical universe, which has this property that if you apply it to an element of the domain set, then f of x, and this is the set theoretical dot. So this really is a graph of a function which at this point takes the first coordinate of a pair and gives you the second coordinate, will be equal to the predefined sort of lambda function. And in this case, you can prove this because the function is bounded. The function lives on this f1 times f2 thing. So it's sort of guaranteed that it's small enough to be in the set theoretical universe. So that's what the proof here would be about. But this is the thing which people in Isabel are enjoying and doing like all the time when they are creating function types, and the sort of Isabel automation automatically knows that the function type is still in some sort of power set of the original sorts. Whereas in Mizar, you do not have so much automation to show this, so you have to use these schemes to bring these objects back to the set theoretical world. So that's also, for example, when the translation to first order logic slightly breaks, because when you are using these schemes, they are parameterized by these sort of second order objects. So then you have to do some sort of work to get it translated to first order logic.
I mean, actually,
sorry.
I mean, this is still first order logic. I mean, the first order logic, the function and predicate symbols are schematic. I mean, it's only things like, belongs to and empty set and so on that have a fixed meaning. You can add uninterpreted function symbols and they are schematic.
Well, you always have to show uniqueness and existence. Adding something uninterpreted in set theory is sort of tricky. You can do it by using something like sorry. Basically, you can say I have this function or this record.
I don't think it's conservative. I mean, you may add a principle that misuses it, but
No, I'm saying how it is in Mizar. Like whenever you introduce a function or a predicate, you have to give that a function.
that's not necessary. I mean, in first order logic, you can have schematic predicate functions.
Well, yeah. So for example, here, but once you are proving things about like you really want to show this, right? Like you want to have things which are proved in your world.
I mean, first order logic is, second order logic with implicit universal quantification. So very simple.
Well, so there are things which are not for free. So here, the F3 indeed becomes like a uninterpreted Skolem function, basically, in this sort of thing, or eigenvariable, or whatever you want to call it. And then this proof is sort of completely first order, because this thing is fixed. But when you want to use it, then you have to do like second order instantiation, second order matching. That's not for free.
It's admissible in first order logic.
Yeah, well, it will not go through Empire, for example.
Yeah, I mean, I think people have been underutilizing first order logic.
Well, if you can explain to the first order automated theorem proving people how to do this, then obviously it will be useful for things like infinitely axiomatized set theory in this case. Well, that's it really. Yeah, if you're more interested, then somewhere down here is that's that's also interesting. Freig is teaching a course in Mellon, which where he has this sort of tutorial in Mizar. One thing there are things about Mizar which are nice. There are things which are not so nice. Like the implementation is sort of oldish, and the source code is still sort of closed and only accessible to the association of the Mizar users. For example, what Bohua was showing looks like a promising way how to port some of these Mizars of typing ideas into some sort of more modern framework.
I think this manual there should be porting still needs to be manual, not automatic.
What needs to be manual?
So porting proofs from Mizar to Isabelle 4 still needs to be manual.
So there is a project by Cezary Kalishik and Karol Pong where they are building something similar
So
to
they're
what you are
trying
doing.
to do it automatically.
Yeah, they are trying to really mirror the Mizar syntax in the Isabelle syntax, but they are not there. They like for example, mimicking the Mizar by like this step is really non-trivial. Like I can reprove every Mizar by with Vampire from like something like 99% of the cases because they are not so complicated. But re-implementing exactly the Mizar by is going to be a pain. if you have something like a sledgehammer, you might be able to go through all the steps. Sorry, or auto too. Yeah, that's it probably.
Wait, so the Mizar is the only known prover which will handle all the buys?
So I got like almost 100%, like 10 years ago when I exported it to Empire, and I tried hard. I got something like 99.9, like something like out of 5,000 proof obligations, I had to do manually like 10 of them. So it's like with some work you can do most of them automatically. Okay, shall we finish the session? Yeah, sorry for that. It's very last time. No idea.
Are you done?
Yeah, mine was the first one.
Oh, okay, I missed it. I came in, I thought, you started at 3, is it?
Two.
No, two.
Oh, okay, I really want to see mine.
Well, hopefully it was recorded, the green light is on, so.
Yeah.
Oh, should we somehow switch it?
Yes, we affect the first